Picture an atom. What does it look like? Most likely it will resemble something like this. A fairly large nucleus surrounded by orbiting electrons whizzing around the nucleus. This image is a popular icon of the atom, but it only vaguely represents our current model of what the atom looks like. First, we're going to travel back a little over 2,000 years ago to the times of Aristotle and Democritus. The Greek philosopher Aristotle believed that matter could be divided infinitely without changing its properties. Democritus disagreed. He thought that matter could only be divided until you got to the smallest particle, which he called the atom, coming from the Greek word atomos, meaning indivisible. So who was right? Aristotle was very convincing and did many experiments using the scientific method, so more people believed him. It wasn't till around 2,000 years later, in the early 1800s, when John Dalton came along and disproved Aristotle. Dalton went on to say that matter is made up of tiny particles called atoms that cannot be divided into smaller pieces and cannot be destroyed. He also stated that all atoms of the same element will be exactly the same, and that atoms of different elements can combine to form compounds. The really awesome thing about Dalton's model of the atom is that he came up with it without ever seeing the atom. He had no concept of protons, neutrons, or electrons. His model was created solely on experiments that were macroscopic, or seen with the unaided eye. Now let's fast forward to the late 1800s when J.J. Thomson discovered the electron. Thomson used what was called a cathode ray tube, or an electron gun. You've probably seen a cathode ray tube without even knowing it. They are the bulky electronic parts of old television sets. Thomson used the cathode ray tube with a magnet and discovered that the green beam it produced was made up of negatively charged material. He performed many experiments and found that the mass of one of these particles was almost 2,000 times lighter than a hydrogen atom. From this, he decided that these particles must have come from somewhere within the atom, and that Dalton was incorrect in stating that atoms cannot be divided into smaller pieces. Thomson went one step further and determined that these negatively charged electrons needed something positive to balance them out. So he determined that they were surrounded by positively charged material. This became known as the plum pudding model of the atom. The negatively charged plums were surrounded by positively charged pudding. A few years later, Ernest Rutherford, one of Thomson's students, did some tests on Thomson's plum pudding model. The members of his lab fired a beam of positively charged particles called alpha particles at a very thin sheet of gold foil. Later on, you'll learn that alpha particles are really just the nuclei of helium atoms. Now, because these alpha particles had so much mass, he fully expected that all of the alpha particles would go right through the thin gold foil. This is because if Thomson were correct about the plum pudding model of the atom, the alpha particles would just go through the positively charged matter and hit the detecting screen on the other side. But something strange happened. Some of the alpha particles went through, and some were deflected by the gold foil and hit the detector in different locations. Some even came straight backwards in the same exact path that they took. Rutherford said this would be as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. After this experiment, Rutherford concluded that these alpha particles must have hit something very small, dense, and positively charged in order for them to come straight back. Rutherford claimed that this also shows that the atom consists of mostly empty space, and that all of the positive charge is not evenly spread throughout the atom, but instead squished into a teeny tiny nucleus in the center of the atom. Finally, we will move forward a few more years when Robert Millikan discovers the charge of an electron. He did this using his famous oil drop experiment, where he sprayed charged oil drops between two metal plates. He was able to prevent the oil mist from falling by balancing out the downward gravitational force with electrical force equal to the charge on the oil drop, which caused the oil drop to repel upward. When these two opposing forces balanced out, he could calculate the charge of an oil drop and use a graph to determine how many charged particles were on each drop, and then calculate the charge of each individual particle. These were just a few of the hundreds of scientists that worked hard to further our knowledge and understanding of the atom. It is important to note that our understanding has been an evolving process, including Aristotle and Democritus's opposing views of the atom. Aristotle believing that matter could be divided forever, and Democritus believing that we would eventually get to the smallest particle called the atom. 2,000 years later, Dalton proved Democritus was correct. Shortly after that, electrons were discovered by Thomson, the nucleus was discovered by Rutherford, and the charge of an electron was measured by Millikan. The picture of the atom you had when this lesson started is still flawed when compared to the current view of the atom, which we will discuss in a future lesson. And as scientists uncover more details about the atom, the model we use to describe it will change and become more and more accurate.